So we are going to now turn to looking at combinations of spaces. Spaces built from other spaces. We looked at a particularly simple example of that, which is if we had a combination of circles. We focused on two, but if you had several similar arguments, we'll tell you that you get a free group. Well, what if you did not have circles, but instead we had, let's take a single base point x0 and a bunch of spaces. Maybe they have some structure. Maybe one of them is a surface like this. Maybe one of them is just a circle, some other spaces here. Okay, this is some other space which has some stripes, whatever you call them. And this one is a spotted space. And what is the fundamental group of this combination? Well, what is clear is that if I look at x equals this, and these are x1, x2, x3, some indices, and we have a common base point, then the fundamental group of each of them includes into the fundamental group of x. And they are independent in the sense, for example, if you want to define maps on the whole space, it's equivalent to defining maps on these. Okay, so that gives you something like the free product, closely analogous, like the free group, sorry. What would we call free products of groups? So this is fully categorical. Let's look at the data. So suppose we are given G alpha and alpha in some index set A is groups, just arbitrary groups. Okay, then the free product is something containing these groups, but it's better to think of them as inclusions. Is, well, it's a group. We'll call it star alpha G alpha. So for example, if we would have just two groups, we would write it as G1 star G2, and we have three groups, we would write it as a binary operation. This is the big version of the binary operation. And for all alpha in A, we have I alpha inclusions from G alpha to the product. So far the picture is what you see here, alpha in A of G alpha. But we want them to be independent. Now in the case of a free group, we saw that we had to specify the value of a homomorphism on each of these loops here. Okay, on each of these loops here. For free product, we similarly specify homomorphisms on each component. Okay, so that is the universal property that we will have of these free groups. So the universal property is we are given a target group H. Okay, and we are given phi alpha are homomorphisms from G alpha to H. This is the analog of having values on each basis element for all alpha in H. By the way, just as functions are assumed continuous, if they are between groups, we assume their homomorphism. So given this and this, there exists a unique homomorphism phi from the free product alpha in A G alpha to H, such that for all alpha in A, we have a commutative diagram. Okay, namely, if I look at G alpha, that's already mapped to H by phi alpha, and it also includes into star alpha of G alpha. I've put it dashed because you can think of solving the commutative diagram. So this diagram commutes. Okay, this is saying that the restriction of the homomorphism to each G alpha is the given homomorphism. We can put these together and in a unique way, just like we have the restriction to a basis. Okay, so we'll see this categorically. I alphas will turn out to be injective, but it's better not to assume them, because that would mean we would have the tricky categorical issue of defining I alpha to be injective in an arbitrary category, and it's unnecessary. So instead we simply say there are morphisms I alpha, so that this happens. We will revisit after constructing the free group and looking at a topological result. We will revisit what this is in a general categorical context, where it is what is called a direct sum or a coproduct. So let's see the relation between free groups and free products. There's a very nice formal relation. It will also illustrate using purely universal properties. We'll go from universal property of one to the universal property of the other without using existence. Incidentally, we haven't yet shown existence of free products. We have of free groups. So S will denote by this angle bracket S is the free group generated by S. Okay, we will see the reason for this when we talk about presentations. So if you have seen them, you know why I use this notation, generated by S. So we have the following proposition. Namely, the free group generated by S is the free product of copies corresponding to the generators of Z. Okay, so I'm going to call this copy Z sub S sometimes. So just integers for these groups. And how would we prove it? Well, we'll show each side satisfies the universal property of the other. Okay, so first of all, we have inclusions which will take so let's look at, firstly we'll see that RHS, that is star S in S, Z, let me call it ZS, is a, and hence the free group. Okay, so the inclusion map will take S. So let me write its domain and codomain. So we have S to this thing, this copy, S in S of ZS. I of S is, remember, part of the definition of a free product is we have an inclusion map corresponding to each copy. So I look at the inclusion map corresponding to each copy and look at the element 1. This is in Z, which is ZS. Okay, and remember, IS is the inclusion map from ZS into the free product. So we have the correct data. Okay, so given, now suppose we are given H and we are given a function f from S to H. Okay, so what we'll do is we'll first define homomorphisms. Define phi S mapping Z, which is ZS, to H in the following way. Here we're using the fact that Z is the free group on one generator. Okay, so we define phi S of N is going to be f of S to the power of N. So this is the homomorphism on Z, which takes 1 to the element f of S. Okay, and then observe phi mapping star S in S of Z to H satisfies the universal property. Okay, so we have S, which maps to the free group by the inclusion map, or if I wish, I'll write it the other way. S maps to H by the inclusion map. Okay, and sorry, not by the inclusion map, by the given homomorphism, which I called F. Then S also includes into the star of S in S of Z, and phi is a map from here to here, and each of these is the inclusion map, so satisfies this thing commutes. So it satisfies the universal property. Okay, so I'll just say that the other way and the uniqueness are similar. You can take these as easy exercises. Not maybe that easy, but they will let you understand the definition. Just in words, the other way is that we have the free group and we want to show it is the free product. So if you have the map on each component Z, well, those are determined by their value at 1. Using that you define, so other way and uniqueness is that we are given, so let me say briefly, so we are given now phi alpha mapping Z, phi for consistency of notation, given phi S, which maps ZS to H. You let F mapping S to H be f of S is going to be, this is just like we did previously, phi S of 1. Okay, so we'll simply send the function on S, the generators, to be the value of the homomorphism on 1, and now you have a function, universal property of free groups tells you have a corresponding function on S, the free group generated by S, and then you show that it satisfies the universal property. Okay, so these are, but this is a nice illustration and it's useful of the connection between free groups and free products. It's also useful when we prove Van Kampen theorem. Okay, but our next task will be to actually construct the free group, which is going to be quite similar to how we constructed free products.